Good morning. I'm Nick Kuftel. Actually, let's get started. We're going to start our webinar today, talking about leak testing automotive EV batteries. So kind of the skill level we're going for, we're calling advanced beginners, something a step above novice. So you have some exposure to leak testing of automotive batteries. We all consider ourselves something well beyond this, but expert level is something that we all strive for and try to attain, but we're all learning all the time. So we hope to expand your knowledge in this presentation today. I'm Nick Huftel. I'm a product applications manager. I specialize in leak testing for our automotive customers and working on custom system applications. Philip, would you like to introduce yourself?
Yes, I'm Dr. Philip Schurig. I'm a market manager for industrial leak testing, which means I cover all of our markets for leak testing and some dedicated regions. And also the battery topic, leak testing, as well as the other steps are one of my focus areas where I spend a lot of my working time.
Thank you. So today we're going to talk about ways to go about selecting the appropriate testing technology or methods for an application. Whoops. Sorry about that. What possible obstacles you're likely to run into, how you can avoid them. And then we have a few examples of actual applications and studies that we've done that we can go over. So this is kind of a broad spectrum look at all the different applications that involve either leak testing or vacuum pumps, vacuum technology, and the production of EV batteries. Specifically today, we'll be focusing on these. We'll be focusing on testing the battery pouches, end-of-line testing of the battery packs, and then also the coolant tests. So we'll start talking a little bit about what leakage or what the causes of leakage are. Nothing is truly tight. Everything is going to leak something at some amount, given some pressure differential. The nature of a defect that will cause a leak could be very different. It could be a pinhole. It could be something that is a capillary that's kind of shown on the screen, something similar to that. There could be something with a much more tortuous path. It could be something as simple as a hair or burr across some sort of sealing surface. Different types of defects will allow different gases or different fluids to leak in different amounts. Porosity is another thing to be very aware of, especially if anything with castings. There could be a multitude of very, very small leaks that perhaps wouldn't leak water, for example, or there could be a capillary that definitely will. And those are the types of defects that we're primarily concerned with today. So our purposes for this testing, particularly with this type of product, are twofold. With any product that you're testing, you care about the quality and maintaining the utmost standard of quality parts that are being shipped, making sure that customers aren't getting bad parts, just from a financial standpoint. But also it's extremely important, especially with these products, to keep in mind that the safety of our customers is very important too. And we have potential issues that can be very dangerous for the consumer, for the end user. So maintaining a high testing standard is very, very important from that standpoint. Philip, you want to talk a little bit about different types of leaks or different ways to look at leak tightness, if you will?
Sure. You mentioned something very important, so high testing standards. Here I want to touch a bit the topic of functional tightness, because high testing standards doesn't mean that you always have to strive for the very lowest leak rate possible. This very easy example to understand is here this potato sack, which just has the functional tightness to ensure that no potato falls out of it. So you can here have a net width of several millimeters, which still is a functional tightness, which prevents any medium from inside the potato sack to get to the outside. Another example, something like 15 orders of magnitude in length scale away from this is an accelerator ring in the R&D world at the CERN. Here you want to prevent that any gas from the atmosphere enters the accelerator ring to maintain a very low pressure. So you ensure that the protons moving around in the circle do not hit with other molecules except the proton which is coming towards the other proton beam. These are two different sides of a functional tightness requirement. And now the question is, how low does a leak rate have to be functional tight for a cylindrical battery cell or for any battery cell? But before we jump into the examples we have prepared for you, another topic of today is how to find the right test recipe. And it all starts with a good pre-selection process. What do we mean with this? So is it important for you to find the leak location at your product or to determine the overall leak rate of your product? These are two different approaches you can have. The next step would be, is your product pressurized over atmospheric pressure? So has it an overpressure related to atmosphere, or is it under pressure related to atmosphere? This defines the gas flow direction. So is something entering your product or is something exiting your product, which you want to prevent? And the third point to consider is the investigation area. This could mean, do you want the total leak rate of your product you want to test, or are you only interested, for example, in a partial area, which can be achieved by just using an adaptation around the feed-through in your product and just test this feed-through instead of the whole product part? Or do you only want to localize, like before mentioned, the leak position? And if you have spent some thoughts about these three key points, then you can cross out already a lot of non-applicable methods and have already a good starting point to further progress in the test recipe generation. Right now, we just want to ask you in the poll, which methods do you currently use for leak testing? Because also in the world of battery leak testing, there are several ones you can use. For example, differential pressure decay or pressure rise, a flow measurement method, a hard vacuum test, a sniffing test, or the direct electrolyte leak detection. We now open the poll where we give you some time to answer one of the answers I just read out to you. So this gives us some impression about the examples we have prepared for later, where we will spend some more thoughts or some more time. So let's see what the results will give. After 30 seconds of poll, roughly 40% of the audience have reacted so far. So let's wait another 10 seconds before we close it. So thank you for your participation in this poll. We want to like to share with you the results as well. And you see here, right now, the winner is the electrolyte leak detection, followed by a sniffing test, and then the third place is shared between the hard vacuum test and the pressure differential test, or an air-based test, let's say. So where do we use the different tests? We'll come in a second when we're talking about the different examples. But let's still continue a moment for the test recipe parameters which influence or should be considered while defining this test recipe. And the first thing to consider is for sure your product characteristics. What is the volume of your product? What is the outer material or the inner material of your product? And do your product have connections for the pressurization or the evacuation of the part to enable it to overpressure for an air-based technique as well as for helium leak detection method? The volume is also crucial to define the chamber size, and the materials should be considered when you size the vacuum pumping group, as different materials have a different outgassing rate, which all contribute to the pump down characteristics or the total pump down time of your system. If you have taken this part into your considerations, Also, the environmental conditions are important. Here we are thinking about as examples of the ambient conditions, so temperature, humidity, the uncontrolled flow which can appear when, for example, somebody opened a door at the factory or a window, or pollution inside of your factory hall. The two first points I mentioned, the ambient conditions and uncontrolled flow, are much more important when we talk about air leak testing, as a flow of cold air over the surface of the air leak testing setup can really alter the result of the pressure decay or pressure rise method, as well as the temperature decrease due to a sunbeam resting on the testing station over the day, or increasing ambient temperature in your production hall because it's summer. When I'm talking about pollution, I don't relate to ISO norms regarding particle sizes, because these are not so important for the leak detection process. Here I'm more thinking about tracer gas pollution in your production hall, which can occur if you have, for example, a welding station using helium-containing welding gases, or some electrical forklifts or electric power tool charging stations. While these two later examples do create hydrogen in this process, which will alter your hydrogen background level when you're using forming gas for leak detection. What do I mean with background levels? So we have a certain background level when using ambient conditions, so normal air. This more or less defines the pump down time to a defined background level in your testing system. And if you have a higher background level than normal, this calculated or defined process time will not be sufficient to reach the background level you require in your process. The background level is important to guarantee a good signal to noise ratio between your measurement rejection level, which is the next important thing while defining the testing demands, and the background level. So the difference here should be, what we suggest to our customers should be at least 1 decade, so a factor of 10. Also, the test pressures should be considered to be as near to the normal operating conditions in the future life of your product, as well as like this in the testing situation. And for air-based techniques, the temperature consistency and the volume constancy is very important, as these really have an influence on the measurement result. What we'll show you later in one example we have prepared for you. And last but not least, process requirements we also have to consider while designing a test recipe in the end. It's initial cost, running cost, cycle time, Industry 4.0 requirements, gauge R&R capability, deterministic or probabilistic measurement method. All these requirements we will not cover in depth in this webinar. We have prepared in the past another webinar where we have already covered this. So I invite you to go to our website in the knowledge section and just watch the latest webinar on these topics. And now I also want to jump into directly the first example of battery cell leak testing. You already have seen here the different formats which we can test for, let it be cylindrical, prismatic, or the pouch cell. Here we can differentiate between more or less a rigid cell format and the soft cell format in case of the pouch cells. But all of these more or less have the same tightness requirement. We always want to prevent that anything enters our interior of the battery pack, because then some reactions between the chemicals inside the battery and the ingressing gas can occur. One potential outcome I will cover in a second on the next slides. Also, the timing of the test is important. When do we test? In principle, there are several positions or points in time during manufacturing where you can test. A very thorough testing strategy would include the empty cells, testing prior to electrolyte filling, and an end-of-line test. This is more or less the 3 positions in tests where you could test. And here we have to differentiate that the pre-filling testing, so when we have not welded our battery cells to close them or filled with electrolyte, we still can use tracer gases, because we are able to fill and evacuate the tracer gas out of the battery cells. When we have filled with electrolyte, this opportunity is gone, as we also do not want to have any chemicals or media inside of our battery which do not contribute to the real performance or active material of the battery. So here we have to rely on something like direct electrolyte leak testing, or to measure the flow rate which comes out of the battery with the flow rate method. I want to start with you today with the pre-fill testing. After this, we will also cover the end-of-line testing, or the after-fill testing, it's called. But now we want to investigate a bit the example of the covers of a cylindrical cell or of a prismatic cell, which are assemblies of several single pieces to an assembly. This means we have some sealing areas which we have to test. And this testing process is more or less similar to the pre-fill testing, when we have inserted the jelly roll into our battery cell, put the cover on top, like in the left blue box, and then we welded the cover to the pack, and then we can test the quality of the welding seam. And the requirement here is, again, that we don't want to have any ingress of moisture, because this can react with our electrolytes inside and cause the formation of hydrofluoric acid. This is a highly toxic gas and very harmful for human beings, as well that it can alter the electrochemistry in the battery cell, with the result of a very low performance and much higher ampere rating, which heats up the battery cell and will have some further consequences later on in the life of the battery. So what is the requirement to prevent any ingress of moisture? Well, humidity can result either in a fluid form or in a gaseous form, while to prevent a gas to enter something is the most strict criteria, which should correlate more or less to a leak rate limit of 10⁻⁶ millibar liter per second. Now I want to jump back a bit into this test recipe creation, which we mentioned before, and show you a chart where we mentioned the three things to consider. First, we have talking about the measurement method and the localization method differentiation, which are here the rows. Next thing was the gas flow direction. So shouldn't it enter your part, or should it go outside of your part? And the list of methods you now will see are coming from the DIN EN 1779, which is a huge list. We don't want to cover all of this right now. I just want to tell you, if you execute what we have told you before for this part of the leak testing, we are interested in the total measurement of the leak rate of a battery cell. So more or less we can cross out all of the bottom localization methods. As well, if we're talking about the 10⁻⁶ millibar liter per second leak rate, this is out of the testing scope, or of the scope of an air-based method. So we also are located in the tracer gas world. We do want to test the flow rate originally into the object, and also in the integral vacuum technique, because we're interested in the total flow rate and not in a partial vacuum or a partial leak rate of the battery cell. So in the end, we only have to consider the integral vacuum technique. Now, I want to show you some vacuum pump down simulation, because this is very important. If you have to think, when you want to test this at the battery cell, you have a schematic like this on the left. We have a battery cell which is in the vacuum chamber. The chamber will be evacuated by a vacuum pump. And we have another vacuum pump which is connected via a feed through to the battery. Here we have a very high conductance loss, or pumping speed loss, because we have to have a connector to the battery cell itself. In this example for the simulation, we have chosen a 5 centimeter long and 3 millimeter in diameter piping to reach target pressure in the simulation, like with the vertical red line, of 0.03 millibar. Why this value? Well, it corresponds to helium partial pressure of 1.5 E-7 millibar. And depending on the suction speed of your leak detection system, it could correlate something more or less to 1 decade difference between the leak rate you have to as a rejection level and the background of your system. But this is not the important part here. The important part is that we, due to the small conductance, to the small thing which is the difference between the similar pumps here, is the development of the red curve compared to the black curve. All of you can imagine or will agree with me that we will have a much longer pump down time to the same pressure when we are considering the suction speed differences between these two lines. Another problem now is that when we're talking about pump down, that the surface of the chamber pump, it's more or less stainless steel for the chamber or aluminum for the surface of the battery cell, while the interior of the battery, it will have the battery cell material, so aluminum, for example. Then it will have the jelly roll surface. It will have a very huge surface which outgasses, for example, and to reach 0.03 millibars is a tough task here. Unfortunately, I cannot show you any real phantom calculation because the kind of the battery size will differ too much to cover all of your needs or products. So if you have the interest here and for some more detailed simulations, do not hesitate to contact us afterwards. Right now, I just want to tell that if you're not able to pump the interior of the battery to that level because of the cycle time, well, you can also think of inverting the test direction. So going from into the object to out of the object. This allows us to reach much higher pressures. So target pressure, for example, 1 millibar in the battery cell, because we only have to make sure that we have a known concentration of helium inside to calculate the real leak rate of the defect we want to measure. Another advantage here is that we will have a much lower outgassing rate, and with this, no real influence on the conduction loss to reach the 0.03 millibar. So more or less the black curve, you remember. And with this, we can say here that it's applicable if you, due to cycle time requirements, if you cannot use the intended direction you want to really prevent in the real life case, you can also test in the other way around. It's not the suggested way of test, but when the outer conditions do not allow it, then it's also a possible way to go. So this is everything I wanted to tell you in this example for the pre-fill testing of a coin cell or of a prismatic cell, so the rigid cells. But what we've heard before, there are also pouch cells, which have a different approach here. And also we want to investigate now a bit the after electrolyte fill testing. So Nick, what can you tell me about this topic?
Thanks, Philip. So on this topic, again, specifically leak testing pouch cells that are filled with electrolyte, the University of Michigan Battery Lab was kind enough to work with us on the study. Just a quick word about them. The University of Michigan Battery Lab, they have an array of manufacturing equipment. So they have pretty much an entire battery cell manufacturing line in their facility. And what they do is they take that and they allow different manufacturers, whether they're startups or more established, to try out different designs, different chemistries, different things so that they can have enough product to test and evaluate new concept and potential next generations of lithium-ion batteries. So in working with them, they worked with us to create bad samples or control positives, if you will, that actually represent defects that you're likely to run into in manufacturing. The benchmark that we used in the past is just testing with a part with a pinhole. Problem is that you're not likely to encounter parts with pinholes in manufacturing. Something that's far more likely is that, the heat welder that's creating a seal on the outside of the pouch at some point, whether it just be, somewhere on a seal or especially where there's a tab, to fail, and perhaps the quality control mechanisms on the equipment doesn't recognize that there's a failure, and you can have a large amount of product that is no good. They created several of those samples for us, which was excellent. And we used those. We tested good parts. We tested the bad samples that they used. We tested good samples along with an orifice to kind of show what we would get from a part that has just a 5 micron pinhole. And we used them with we tested them with two different methods. We used mass extraction and we used a residual gas analyzer. So the picture on the top left, we have a picture of two bad parts. One of them has got a bad tab. So where the seal around the tab is not complete, so you have some length of the tab is not sealed, and there's a good amount of access or ability for electrolyte to leak out. We did the same thing with seals at different points to create similar sized defects. Again, these are fairly large, but they would still represent a potential problem in manufacturing, a type of defect that you are actually potentially likely to encounter. The first step is we took these parts, we placed them inside a vacuum chamber. We performed a quick 15-second mass extraction test. That's just to determine a go, no go, just a fast test just to show whether the parts are good or bad. And then in conjunction with that, we also did a residual gas analyzer test, a multi-gas sniff test, if you will, to look at the gases that were coming out. And we used that as a verification that there wasn't some other problem, or to prove that the leakage that we were measuring actually represented electrolyte leaking out of the part. So we went through and tested all of the control negatives, so the good samples first, and using our mass extraction equipment, all the samples, we got results that are very similar. Not a whole lot of variability between 15 and 20 micrograms per minute. Sorry, having trouble with the controls on here. Then we tested the bad samples, or the control positives. They all gave a gross leak, or at least a full scale result, very quickly. We would be able to do this test even faster than 15 seconds. It'd also be possible to batch a lot of these together, but we were showing that it's possible to get a go, no go, pass, fail result very, very quickly. Now the data using the RGA, our residual gas analyzer, we used an OmniStar in this particular instance. Just measuring the background, no leakage. We had extremely low incidence of these gases in atmosphere, if you will. We're all in the 10 to the minus 11 range. And then when we took a measurement after the mass extraction test, we did this two ways. So one way was at the immediate end of the mass extraction test, we would wait some amount of time for any leakage, because as the electrolyte is boiling and the gases were coming out of the pouch, we measured the difference in readings from the RGA. And then also we would then purge the vacuum inside the chamber and then take another measurement. So this shows the results of those. And the best result is after purging the vacuum and then taking a measurement immediately after that, we would get results that, for the instance of the bad seals, their measurement was 1,500 times more than the good samples. It's a very dramatic difference. For the bad tabs, it wasn't as high, but still very, very, very large difference between good parts and bad parts. It was possible to get an extremely definitive test, an extremely high level of confidence. Using the residual gas analyzer, you can be very certain that if you're shutting down your line, it's because you actually have a manufacturing problem. You're really making bad parts. It's not just a bad piece of tooling that's allowing some leakage. So we're going to do another poll. I want to ask each of you at what stage in component manufacturing you're doing your leak testing. Are you doing empty cell or pack testing? Are you testing the cell prior to electrolyte filling? Are you filling the cell prior to formation? Are you doing an end-of-line electrolyte test? What type of test do you guys do right now?
If you choose the other option, please don't hesitate to put it into the chat function, which method you're using. And I also see that you have some risen hands here. We won't answer to the raise hand feature here, but please also put your question into the chat function, or the question function, and we will answer it at the end of the webinar and the Q&A session. Thank you.
Okay. Go ahead and show the results. Okay, so most are testing the cells prior to electrolyte filling. Last place is tied between an empty cell or pack or other. Oh, I'm sorry. And end-of-line electrolyte leak test is the most common. I apologize. Okay, very interesting. So end-of-line leak testing for the fully assembled pack. Actually, Philip is going to get into that a little bit more later. And before we discuss that, we're going to talk about the coolant test. So a quick study that we performed, just trying to simulate a coolant channel test. We used just a tank. So coolant channels, it's all rigid piping or heat exchangers. So it behaves very similar to a tank. I used a 5-liter volume that's fairly representative of a very large battery coolant system. Many of them are smaller, 1 to 2 minutes, so the test can be performed much faster. 2/3 of an SCCM at roughly 2 bars gauge seems to be fairly common specifications, although there is some variability. So the purpose of the test is I'm testing that volume, and then we're adding a defect that's going to flow at our reject limit or very close to it at our test pressure. So this shows with no part volume at all whatsoever, just testing the orifice only, we're able to very quickly, in a matter of seconds, measure our flow rate. As you add volume, that reaction, that response slows down. So 5 liters, again, that's kind of on the upper edge of volume. So this is about as long of a test as you'll run into. But with just kind of taking an extreme example, went out and did a 6-minute long test, did a very long fill, about 3 minutes, and then 3 minutes of measuring. The blue line represents the background measurement just from testing the tank by itself. The flow is not zero, even though the tank is not leaking, just because the pressure inside the tank will asymptotically approach its set point. And the longer you test, the closer it gets to that set point or to that test pressure. And so the less flow you'll be measuring going into it during the measurement steps. Obviously, you want to have it as short as possible. So we took that amount of fill time and then measurement to see how a good part would react. And then I ran the test again with the orifice added or the defect added. And so we're looking at how much of a difference we get between those two samples. So with some more work and some more optimization, perform the same test in less time, about 4 minutes. And this shows an acceptable amount of separation between a good sample and a marginally bad sample. So we can certainly test a very large coolant system in 4 minutes or less. The faster it can go is obviously the best, or the faster the better. But the amount of time that'll be taken just for testing the pack itself is going to be on the order of this amount of time or longer. So Philip, what else can you tell us about other methods of testing that may be more applicable to the end-of-line testing of the pack?
Yeah, thanks, Nick. So when we have tested the cooling channel, we also think about testing the complete battery pack, which is also very crucial as it is mounted in the bottom of the car. So we want to investigate again a bit the requirements versus the impact. So for the example, we have chosen a 200-liter volume, which is too comparable, to be honest, a rather extreme example here. In the real life, you can face something like 100, 120, or even smaller, as well as the allowable differential pressure of these battery packs. They can vary between 50 and 100 millibar or 50,000 to 100,000 pascals. So we have chosen here the example for intermediate pressure differential allowed. Also, when we're talking about examples and ranges which are applied, it's also applicable to the tightness requirement. Quite common in this case is an IP67 rating, which means dust proof as well as the immersion under 1 meter of water for 30 minutes, so no water will ingress the product tested. But we can face also stricter tightness requirements or even a bit looser, so much higher leak rates. For this example, we just want to stick to the IP67 rating, which more or less correlates to a 5⁻⁴ Pascal cubic meter per second rejection level, or 5⁻³ millibар per second, or 0.3 SCCM. When we now take into consideration the 200-liter volume of this example and this leak rate in Pascal cubic meter per second, we can translate this to a common pressure decay rate. So it would be a 2.5 E-3 Pascal per second pressure decay rate, and over a total measurement time of 150 seconds, it would mean we have a total pressure drop of 0.375 Pascal. One could think, well, with the technology I have at my testing lab, this is easily measurable and I will have no problem. This might be true, but we have mentioned before in the presentation that the environmental conditions have to be considered. And I want to show you here that even very small influences have a dramatic impact into the measured pressure of the system. So even if you have a pressure difference of 0.1 degree, you will have a wrong reading of 37 Pascal. So this is the impact of a temperature variation onto the measured pressure of this kind of battery pack in this example. So a factor of 100 bigger than the actual leak rate you're testing for. Also, a volume variation of 0.1 per mil, so 20 milliliters compared to 200 liters, which could be caused by some movement inside of the battery pack or not optimal laying battery pack on the test chamber. All of this will also already induce a 10.8 Pascal pressure reading on the device, so a factor of 33 higher than the total pressure drop you want to see. This means that for this extreme example of an IP67 rating at a 200-liter volume, air is not a real solution to test for. If you go to much smaller battery sizes and to a more easier test tightness requirement, still air testing might be applicable, but still, well, on the edge, it might be narrowed as suit with the hot needle. But there are other opportunities which you can use for leak testing a finally assembled battery pack, which is the helium sniffing method, which was mentioned by some of you also in the beginning of the webinar as a already used method. So we see here a battery pack which has an IP67 requirement, and you can test it in the way that you are pressurizing your battery pack with the helium concentration, and then moving around one sniffer probe guided by a robot arm, or several sniffer probes around your product. The problem now here is, in this example, you really see there is no real inlet into the battery pack. And that's the real life challenge one will see, because it's important to achieve a homogeneous helium concentration to really find the leaks. Something of a problem is as well that we only have a 70 millibar pressure differential allowed. So if we evacuate first to -70 millibar gauge and then pressurize with 100% helium to +70 millibar gauge, we will achieve something like a 13% of helium concentration. When we correlate this or take this diluted tracer gas into consideration when calculating the leak rate rejection level to be found, we result with a 6.5 E-4 millibar liter per second leak rate of the defects we have to sniff. This is no problem. Depending on the suction speed of the sniffer probe, the background should be at least 1 decade lower than this. So this will be possible to measure. But the problem will be, again, the homogenization time, because the dilution of the helium we consider here in calculation assumes that we have everywhere in the battery pack a 13% of concentration. This is hard to achieve. I will show you in an example on the next slide. And also the movement speed of the robot arm to achieve reasonable takt times or cycle times of the battery manufacturing line could be a problem. But let's start first with the homogenization time. In this year's technical seminar of the German Society of Non-Destructive Testing, a very interesting study was presented about gas homogenization time. For sure, the example chosen here was not a complex battery pack, but it was a 2-meter linear pipe where on the one side, a vacuum pump first evacuates to a target pressure, then it will be refilled with 100% helium and concentration to some tenths of millibar over pressure. Now on the other side of this 2-meter pipe, a capillary leak will leak into a leak detector and the leak rate will be measured. What you see here on the y-axis is the equilibrium distribution in percentage, which means the value measured at the leak detector side of the finally resulting equilibrium distribution helium concentration. So it doesn't mean with 100% that we have a 100% helium concentration inside. It means that we have achieved the 100% target distribution percentage. So in our example, it would mean 13% of helium concentration are measured on the other side. What we see here already, when we have a look at the orange or the black line, which more or less is the range where our target pressure will be in between, is that even after 20 minutes, we have not really achieved 0.1% of equilibrium distribution, which is a very bad result for us because it means we have to wait for a long time to really achieve the concentration we want to face. The problem is here, we cannot really define an analytical model. So the industrial approach is to prepare the battery pack with calibrated leaks at different positions and just measure the time it needs to really find all the prepared leaks with a sniffer probe moving around the product to be tested. You can clearly fasten up the homogenization time instead of filling over only one port to use multiple port fillings to shorten the homogenization time because you have several inlet positions and this way easier distribution inside the complex part system in the battery pack. So this is one part of the time of a cycle time calculation of a battery pack testing, but the other hand would be the movement of the sniffer probe. And here we have some cross dependencies, this distance and the speed. If we have a look at this graph here, we did some experiments with the helium leak in the 10 to the minus 5 millibar liter per second range. And we had a probe moving around along this leak in different distances and different speeds. And you see here that the probe was able to find the leak, but the faster it moved around or along the leak rate measured was getting smaller and smaller. And this is important because with the increasing speed of the robot arm, the distance has to be increased to prevent the probe hitting into the surface of the battery pack because the regulation cannot move or regulate fast enough when it doesn't know what comes next. On the other hand, what you can also change still is the suction speed of the sniffer probe. You see here again, the suction speed correlates to the probe speed. And we see here on the y-axis the leak position delay, which means how many millimeters after the real leak we will have the signal on our sniffer, on our leak detector display. You see here, the higher the suction speed, the faster we see the smaller the leak position delay is compared to the probe speed. But another drawback of, so now I can think, well, I go with as high suction speed as possible. But the drawback here is that first, also the background level will increase in your system or the regeneration time, which I mean, when you really face a very gross leak with your probes, so a very high leak rate, you will suck in a lot of helium into your system, and depending on your device, it will cause you maybe to miss the next potential leak when it's too near to the last leak because your device has not regenerated fast enough. Just that much to the topic of helium sniffing. Now, the last part before we finalize our slides. Our presentation is the question, which leak rate requirement do you test for your packs? Is it something like an IPX9K, so high water jet pressure testing, washing, which means 0.006 SCCM? Is it an IP67 rating, 0.3 SCCM, or something much higher, like let's say 10 SCCM? So the audience is voting, going forward. We have a 25% participation rate right now. Maybe some others will react here as well. Let's wait for another 10 seconds before we close the poll, because not everyone here maybe is related to end-of-line pack testing, so it might not be that everyone rates here. So let's have a view on the results. Okay, the majority of the participants uses other leak rates, so neither IP67 nor 10SCCM. So if you're not, if you can share with us, we would be happy to learn about it. If not, then the most common one of the ones to be chosen is the IP67 rating. Now with these results shown to you, I just want to come back to the test recipe generation. We have covered this topic here, but after this, when we talk about real leak rate testing in the production environment, one has to consider something else. And what is really important here is the upscaling. How do I get from a lab scale to a production scale? There are different things you can do. You can do laboratory testing where you utilize some application lab from production specialists. You can try to reduce the cycle time by different means. Let's say free volume decrease, optimization of the surfaces, correct pumping system dimensions or sizing of the suction speed. In the end, this all contributes to a cost or to cost savings, as initial costs or running costs are always to be considered in a high production environment like this in the battery world. Here again, one can say often the initial costs are considered the most important ones, but the running costs can be the major share of the cost of ownership assumption or assessment. So here one can save a lot of money with energy efficient pumps or helium recovery systems, for example, but this will mean higher initial costs and will need another calculation. If you're interested in this topic, again, I can just tell you, we have covered this in another webinar and I invite you to join to watch this webinar as well. And if you need some help for application testing, we have 4 labs worldwide in Germany, France, the US, and China, or we can help you with feasibility and cycle time studies using all of the shown technologies from today. If you're interested here, also don't hesitate to reach out to us. We would be more than happy to help you with our application labs. And with this, I want to finalize here with the key takeaways. When we have spoken about the cell level testing, we said more or less that rigid cells can be tested with helium and RGA methods, and the soft cells are capable of to be measured by mass extraction RGA methods. After the cell level, we're going to the module level and also battery pack level when talking about cooling channels. Here, Nick has shown that air-based methods can achieve a very good result in a very small amount of time. And end-of-line testing of battery packs, we try to cover both air-based method and helium sniffing to tell you something about the advantages and disadvantages. On the right, you see again all of the different parameters which have to be considered when you want to define a good test recipe. And with this, I want to thank you in the name of Nick and myself for your participation in our webinar. If you want to receive the presentation, please write it into the chat function and we will be happy to share the presentation afterwards with you and to get into more discussion. And now, if you have any questions, also don't hesitate to put them in the chat. Let's wait a small moment for those who have a question. We are typing it right now. So one interesting question we have received, Nick. So from your opinion, is there already somewhere a standard which tells you which test procedure to use? Are there standards you know from, or are there some under the way?
So SAE is in the process of a couple different studies and standards, or the creation of a few standards to kind of delineate that right now. Right now, you kind of have to look at what leak rate you're looking for, or what what size defect and what leak rate you're trying to detect, and then you have to pick a test method based off of that.
Okay. So another thing which was questioned is if it makes sense to specifically design some testing ports while product designing, for example, for pressurization or for the air leak testing world or helium world. Do you think this is reasonable?
I think it absolutely makes sense. I mean, having a good port to connect to and perform the test on would be outstanding. Right now, commonly, there will be some electrical port or connection or a vent port, and it'll be connecting to those and trying to perform a test. And there's all sorts of conductance issues along with other problems that make that difficult. It really inhibits flow and it slows down a test, and it creates other issues that could create, false positives, for instance. Having a port with more or less a quick connect or something similar that you can connect to perform the test would make it much, much easier. Certainly much faster, and you'd really cut down the amount of false positives that you run into during testing.
Okay, yeah, well, right now I'm also of that opinion, but it's not that desired to have a port only used for testing, because otherwise it doesn't have any future reason to be there. But well, if you want to save cycle time or produce more in a certain time, this totally makes sense. Also, like I said, to achieve better results. And can one give a generic cycle time answer if you want to calculate or for a battery leak testing or on the cell level? What do you think? So, or let me first answer my opinion before you can contribute. I don't think you can say something generic, because it really depends of how many battery cells you test at the same time. You don't have to rely on a single cell testing. You can do a batch testing from a number of 2 to 200. It really depends on your process. And this totally alters the surfaces you have to evacuate, the size of the chamber. So it's really not possible to tell you a cycle time or also the cost correlated to this with the potential reworking station. That's my input here for the cell testing of rigid cells. What about pouch cells next? Any experience here?
Yeah, so from the study that we did, we were doing a test in 15 seconds. And, after kind of going back and reviewing on that, I think we could have done that significantly faster. So kind of speaking to what you said before, Philip, we were testing one pouch at a time. And obviously, the more pouches you have, the larger the chamber is going to need to be, increasing your volume. There's more surfaces that have to degas. That would all add up. But certainly the increase in time required would not double if you go 2 cells. It wouldn't be 10x if you have 10 cells. There certainly would be an advantage to batch testing. But really what it's going to come down to is you kind of have to look at your volume and kind of calculate how long it would take to evacuate that volume down to, something 10 millibar or less. And then from there, give yourself a couple seconds to take an actual measurement and either look for flow or pressure change. And that'll give you kind of a minimum amount of time that you're going to require or need to perform a go no go test. Now, if you want to incorporate the sniffing test, the residual gas analyzer, to actually look at it and prove that your leakage that you're measuring is really because of electrolyte boiling and leaking out of the cell, and not merely a bad chamber feel or something like that, something silly like that. It's definitely not a false positive. That's going to add some more time, and that's going to depend a lot on how the system is configured. But it really shouldn't add more than another 5 seconds or so if done in a reasonably logical way.
Okay, this is already very, I think, useful information for our audience today. And with this, I have to admit that was also the last question. Again, if you want to receive the presentation, reach out to us in the chat function or via different other channels. And again, I want to thank you for your participation. Have a nice evening or have a good day, depending on the time zone you're in. And well, see you in the next time. Thanks. Goodbye.
Bye.